Okay, so in this problem, we have a daredevil or something who's going to perform a stunt here. They're in this box and been pushed up against this spring. The spring's constant. The spring constant is K. The spring has been compressed in a distance x from its equilibrium position. All right. As soon as the system is released, the spring is going to push the box. The box is going to slide across this distance d, which has friction. Okay, so we've got this friction going on during this distance, but then it hits this smooth, frictionless ramp, which goes up, whoop, and the guy goes flying into the air. We are wondering, what is the velocity going to be when they're up at this height, whatever it is, right? So we're going to say we know h, we know d, we know mu, we know x, we know k, and we know the mass. So pretend I gave you numbers. And we want to find what is the velocity v going to be at this height, given all of this information. All right, so this is quite a problem. Looks like quite a problem. It's not that difficult if we use the conservation of energy, right? So I like to start these problems like this. The final energy will be equal to the initial energy plus the work done by non-conservative forces. So you need to understand, you need to have learned about potential energy for this video. All right. So we're going to break these things up into their possibilities. So we have a spring in this problem, so we might have to deal with potential elastic energy, which recall is defined as 1/2 kx squared, where x is the distance the spring has been compressed and k is the spring constant, just as I've labeled them in the problem. Also, we have a problem where we're increasing our height. The height is changing, so we're probably going to have to use gravitational potential energy, which is mass times the acceleration due to gravity times how high up you are. Kinetic energy is also involved because we have a velocity. Kinetic energy is 1/2 mv squared. And we might have work in this problem. And recall that work is equal to the force that's doing the work times the distance that the force is happening times the cosine of the angle between the force and the distance. So all of these definitions should probably come in handy. Move them off to the side here. Okay, but back to our conservation of energy equation statement right here. So this is these E's are the total energy. So the final energy will have, or could have, final kinetic energy plus final gravitational energy plus final spring energy or elastic energy is equal to initial kinetic plus initial gravitational plus initial elastic plus the work done by non-conservative forces. Phew! All right. So now we might not actually have all horrible 7 terms. Let's see if any of them might be 0. One thing we need to add to our picture is, what do we consider the height of 0? That is something we need because, well, if we're talking about a height h, we have to know with respect to what. So let's just call the ground here the height of 0. Okay, so anything on the ground is 0. I probably shouldn't call it h, but so anything on the ground is at a height of 0. Okay, so, well, the box is on the ground in the initial picture, right? So initially it's at a height of 0. And if the height is 0, that means the gravitational potential energy is 0, right? Because if you put a 0 here in height, then that would zero out potential gravitational energy. So that means that because the height is 0 initially, the gravitational potential energy is 0. Okay, so we got rid of a term. What else might be 0? Well, what about in the first place? Isn't it have no velocity because he's been pushed up and he isn't let go yet? As soon as somebody lets go, or however this works, the thing's going to go flying. But before they do, the velocity was 0, the initial velocity, I'll say. And, well, if velocity is 0, then kinetic energy is 0, right? So because the initial velocity was 0, the initial kinetic energy is also 0. Now, as for the initial spring energy, well, I don't think that's 0 because we have compressed this spring in, right? And so it is storing energy. Over here, let's see. Well, after the spring has been released, and we're looking at the end picture here, the guy's flying through the air, well, the spring is no longer compressed, right? Or in other words, the x, the amount the spring is compressed, is 0. So if x is 0, the spring energy is 0. Or you can just realize that, well, if the spring's not compressed, it's not storing any energy. So the final energy stored in the spring is 0 because x is 0. Okay, but in the end, though, it does have velocity, right? And that's what we're looking for. So there will be kinetic energy, and there will be gravitational energy because he's up at a certain height. And as for the work done by non-conservative forces, well, let's see. There is friction. Friction is a non-conservative force, the only one in this problem. So let's rewrite this. Kinetic energy plus potential gravitational energy is equal to initial elastic potential energy plus the work done by friction. Okay, so we can plug in definitions here. This is kinetic energy, which is 1/2 mv squared, so that would be that v. Final kinetic energy is 1/2 mv final squared. Remember, v is what we're looking for, so I'm glad it's there. Plus, okay, the potential energy, that's m times g times the height you're at. And yes, I called that h. Okay, that's going to be equal to the initial spring energy. So the initial spring energy is 1/2 k. K is the spring constant. That'll be given to you with a spring. 1/2 k x squared. So x is the distance that the spring has been compressed in, and I did call that x already in the problem. Okay, plus the work done by friction. So remember that work is friction times distance times the cosine of the angle between them. So we can put that in for the moment. Friction times distance. I did in fact call that distance d, how convenient, times the cosine of the angle between the friction and the distance. Okay, so the force of friction is not something that I was given. See, all these things in the top, except maybe the V, are things that I was given. Now, I don't see the force of friction up there. So we have to find out what the force of friction is, and for that matter, what this theta is. So I'm going to do a free body diagram of the box as it's sailing through the friction area there. So it's got the force of gravity downward, it's got normal force up, and it's got friction pointing behind it. And just for reference, recall that it's heading in this direction. This is the displacement vector. The direction of the displacement vector is that way. Okay, so, well, we know that the definition of friction, if we're interested for here, the definition of friction is mu times n. Okay, we do know mu, but we don't know n. So from the free body diagram, we can get n using the sum of the forces in the y direction. Okay, where y is up. Sum of the forces in the y direction is mass times acceleration in the y direction, and in this case it's 0, because it's not accelerating up or down. Okay, and that's equal to the normal force, because it's pointing up, minus the force of gravity, because it's pointing down. But recall that the force of gravity is just mg, and so rearranging this, we get normal force is equal to mg. So the force of friction is equal to mu times mg, because that's normal force. And as for the angle, so we've got the force of friction. Now as for the angle between the friction and the distance or displacement, it's 180. See that? They're both laying flat, but it's not 0 because they're pointing in the opposite direction. So the angle between the force of friction and the displacement is 180. Okay. So, let's see, shall I rewrite this? I've got 1/2 mv squared plus mgh equals 1/2 kx squared plus, okay, the force of friction is mu mg times d times the cosine of 180. Oops. Now the cosine of 180, that happens to be -1. So I think I'll plug that in. And I get 1/2 mv squared equals oops, sorry, 1 half mv squared plus mgh is equal to 1 half kx squared, so minus mu mgd. So instead of the cosine of 180, I've put in -1, because that's what the cosine of 180 is. Alright, and so we know everything in this equation except for the velocity v. We know the mass, we know the spring constant, we know the coefficient of friction, we know the distance it goes through the friction, we know the height that it flies up to, and so we can now solve for v, which is that velocity that he's sailing through the air at. I'll go ahead and leave that as an exercise to the viewer, as they say. So we've used the conservation of energy to solve this problem. The problem seemed like it was going to be very difficult with many parts, but we actually did it in one step, didn't we? We didn't, for example, find what his velocity would be after the friction and then use that to find what his velocity would be once he's in the air. No, with the conservation of energy, using energy methods, you can often solve problems in one step that would have taken you multiple steps using kinematics. And that's about it.